Welcome to one more video of Unlevel Electronics Lab. And in this video, design and demonstrate a circuit using Opamp to amplify the input signal, including the DC by 10 times with 180-degree phase shift. So since you're asked to design an amplifier which can amplify the DC also by 10 times with a phase shift of 180 degree, we are looking for a design specification of AV equal to 10 volt per volt and a phase shift of 180 degree. So we know that we have to rig up a inverting amplifier using Opamp. So we are not considering the A naught of this in the calculation of R1 R2. We are assuming A naught to be infinity here. So the expression for gain of this inverting amplifier happens to be minus R2 by R1. So now since we want to have a gain of 10, so this minus corresponds to a phase shift of 180 degree. So we shall assume the value of R1 to be 1 kilo ohms and R2 as 10 kilo ohms. We can actually apply the input voltage even from a DC voltage, and we are supposed to get an output voltage which is 10 times more than that. So while applying the input signal amplitude, we have to be careful the output should be well within the saturation voltage. And even we can apply a signal of any frequency, either sine wave, square wave, anything. Make sure that the output doesn't exceed the plus Vsat minus Vsat depending on the supply voltage. Next circuit is, it is asked to design and demonstrate a circuit to generate a triangular waveform from a square wave. So the input given is square wave, the output expected is a triangular waveform. So we are looking for an integrated circuit. So this is a circuit diagram. Only condition is that the RC time constant, that is R1 into C time constant, should be far greater than T. So you can assume R1 to be equal to R2 so that the gain is equal to 1 here. So the input applied is a square wave. So we are expecting output which is a triangular waveform. So only condition is that R1 into C should be half or greater than T, where T is the half of the time period for half of the total time period for one cycle. And in the second case, we are asked to design and demonstrate a circuit to generate spikes from a waveform, a square waveform. So we are looking for an input waveform which is square wave. The output should be spikes here. So this is what we are expecting. And this is the output of a differentiator circuit. So here we have R into C. Actually, this R1 into, so actually this is R2 into C. The R2 into C should be far less than T. This is actually R2. R2 into C should be far less than T. So once we are maintaining that condition, R2 into C far less than T, we're going to end up with spikes coming here. So you can assume R1 equal to R2, but R2 into C should be far less than the time period here, what is half of the time period for the entire cycle. And conduct an experiment to estimate the slew rate and the unity gain bandwidth. To estimate the slew rate, you can simply apply in this circuit diagram, you can apply a square wave or a sine wave. Whether you apply square wave or sine wave, we know that this is like a zero crossing detector. Once the input voltage crosses zero, so output makes a transition from plus Vsat to minus Vsat. If we expand the time axis, we'll certainly end up with this type of output response. Now this is del V, this is del T. So delta V by delta T happens to be the slew rate. So typically this is in terms of hundreds of millivolt per microsecond. So this is what we are supposed to find out. And in order to find the unity gain bandwidth, so in this circuit we can switch the frequency from a low frequency to high frequency. So with an amplitude something like 1 volt as the input voltage. So 1 into 10 happens to be 10 volt. So make sure that suppose if your supply voltage is 5 volt, you may have to apply lesser voltage, maybe 0.1 into 10 happens to be 1 volt. So make sure that output voltage doesn't exceed the plus Vsat minus Vsat of the power supply, whichever you are using. So we know that at higher frequencies, because of the internal capacitance, the gain reduces. The frequency at which gain becomes 0 dB or gain becomes unity is nothing but the unity gain bandwidth. So we have to actually estimate what is the frequency at which gain becomes 0 dB or 1 volt per volt. Next is the Arduino based experiments. So now here we are asked to write an Arduino script to sense the signal from a temperature sensor and to turn on a motor, DC motor, if the temperature exceeds 40 degrees centigrade. So we are looking for the input coming from a temperature sensor, and we are supposed to operate the DC motor. If the temperature exceeds 40 degree, we are supposed to turn on the DC motor. So here the design specifications are, we are looking for a sensor which is a temperature sensor. In this case, what we are using LM35. The actuator is a DC motor which is operating at 12 volts. The task is turn on the DC motor if the temperature exceeds 40 degrees centigrade. This implementation is done using the Arduino board. The output signal from a temperature sensor has got a sensitivity of 10 millivolt per degree centigrade, meaning for every degree centigrade change in the temperature, the output voltage changes by 10 millivolt, which is from the data sheet, and DC motor rating is 12 volt DC. So we know that output voltage of a temperature sensor for 40 degrees centigrade, so with this sensitivity happens to be 400 millivolt. Now we are supposed to write the script now. For that, note these points. So Arduino should read the analog value from the sensor. Because the value that is coming out from the sensor is analog in nature, we are supposed to configure the Arduino board such that it should read the analog voltage, and therefore LM35 output must be connected to one of the possible 6 A0 to A5 pins of the Arduino, because Arduino board has got 6 IO pins which can 6 dedicated pins which can accept only the analog signal. We have to connect to any one of them, that is either from A0 to A5. And the third point is analog voltage right from your external source varies from 0 to 5 volt. So this whenever the Arduino reads any voltage, so it will be displayed as 0 to 1023 values. 0 corresponds to 0 volt, 1023 corresponds to 5 volts. So therefore 400 millivolt corresponds to 81.84 is the actual value that is coming into the Arduino board. So the red analog value is compared with 82. So whatever value that we are getting from the temperature sensor is compared with 82, because this 82 corresponds to close to 400 millivolt. So this 82 right from the analog voltage from the Arduino board corresponds to 40 degrees centigrade. If the temperature exceeds 40 degree, so Arduino should give a logic 1 on one of its digital IO pin to activate the relay to turn on the DC motor. So once the voltage right from the temperature sensor goes above 400 millivolt, which is nothing but goes above 82, so the Arduino should give a logic 1 on one of the digital IO pin, so that it can activate the relay which is actually driving the DC motor. This is the Arduino board, how it is looking like now, as you can see now. So these are the dedicated power supply thing. We have 5 volt power supply, ground, and we can actually give the input also. Now you can see we are talking about A0 to A5. These are the analog inputs. So any one of the pin can be used as analog input. To any one of these pin, the output from the temperature sensor is connected, and you can see there is a digital IOs, so that is 0 to 12. So in any of these pins we can use it as 0 to 12, 13. So we can use any one of them as the output pin as well as the input digital IO pins. Now this is the driver IC which is used to drive the motor now. So this is a 16 pin IC. So it has got one enable which enables two non-inverting buffers. So there is a 1A and 1Y. So this is the input for the buffer, this is the output of the buffer. This is again the input for the second buffer, output for the second buffer. Similarly, we have it for the other two buffers. Now only one enable is there for both the buffers, and we have VCC1, VCC2. VCC1 is for operating this particular IC. VCC2 is the one which will actually drive the driver which is connected to this driver IC. Now as you can see, this is the pin function. So VCC1, now this is the most important thing, VCC1, which is 16, 5 volt is connected. This is for the internal logic translation, whereas VCC2, the pin number 8, should be connected. It's a power VCC for drivers, which can vary from 4.5 volt to 36 volts. Now whenever we are connecting any relay to the L293D, so VCC2, that is pin number 8, should be connected to a power supply, which is an external power supply, whereas VCC1, which is pin number 16, can be connected to the Arduino power supply or the Arduino power supply itself. So we can connect this to Arduino power supply itself. And we have got this is the enable for 1 and 2, which is 1 here. So if you want to enable that particular non-inverting buffer, you have to give logic 1 on pin number 1. Now we shall actually see the circuit diagram. So one of the possible option 1, that is choice 1, is we have LM35, which is a 3-terminal sensor. So we have one connected to VCC, the other one is grounded, the third pin is connected to the Arduino board. Now this is the output, which will be connected to either A0 or A0 to A5, any one of that. So that's what we saw in the previous Arduino connection. Either we can connect it to A0, A1, A2, A3, or any one of these 6 pins. So that's why it is given as A0 to A5. And one of the digital I/O pin is the one which is going to give the output of digital output. You can see it is connected to the input of L293D. So this one is connected to +5, meaning that the non-inverting buffer, first 2 buffers are enabled. Now it is enabled. Now you can see pin number 16 is again connected to 5. So this 5 and 5 can be connected to the Arduino itself. So this is for the logic. Please have a look at this 8. 8 is connected to +12. So this +12 is actually connected to an external power supply. And you can see this 4, 5, 13 and 12 are grounded here. The output of this non-inverting buffer is actually 3. So this 3 is connected to the relay. So you can see now this is the motor. This motor will be now what we are supposed to do is, now this will be off because this is not nothing is connected to this. So motor is actually off when it is in normal condition. When the voltage becomes high here, when current flows through this, it energizes. This will be get connected to this. So this motor starts running whenever the temperature exceeds 40 degree. Whenever temperature is less than 40 degree, the voltage here is 0. The current flowing through the relay is 0, so that this will be there in NC condition. The motor is not running. Once the temperature exceeds 40 degree, this gives a 1, so which makes the current to flow through this, which will make this to be get connected to this. So once it is connected to this 12 volt will go through this motor and it will be turned on. So as you can see here, all +5 volts are connected to, all +5 volt is connected to +5 of the Arduino board, whereas +12 is connected to an external power supply. This is most important. All grounds of the Arduino and the external power supply must be connected to each other. So if you don't have this ground and this ground common with respect to the Arduino and the external power supply, the motor will not be running. So it is very much necessary that we will be connecting the grounds of the external power supply as well as the ground of the Arduino board. So this is the second choice. So where you can use the transistor as a driver for this relay now. So the same connection, now it is connected to the base of the transistor, which will energize the relay if the base is 1. So otherwise it is off. Now this is a possible script now. Now you can see we are using pin number 12 as the output, which is now defined here. And we are setting a serial port so that we can actually read the value from the LM35, and the analog read value is compared with 82. If it is more than 82, you are writing a high onto the motor. If it is less, you are writing a low. So if it is more than 82, so it will energize the relay, it turns on the motor, and you can see motor is running. So this serial.println val will actually indicate the value of the temperature sensor on the serial port. which is interesting so that we can easily monitor.